Hello, this is my video presentation about the resonant phase matching between a light wave and the free electron wave function, which is an article by Raphael Dahan, is the famous scientist in this field. So I would love to begin with the introduction. So we can say with the confidence that the quantum light matter interactions of bound electron systems have been studied extensively recently. Uh, so comparing this with the quantum interactions of free electrons with the light have only become accessible in recent years, uh, which is not quite obvious for us how to use it. So following the discovery of the photon-induced near-field electron microscopy, also called as it PINEM, so PINEM, we'll call it PINEM. So far, the fundamental free electron light interactions in all PINEM experiments or studies which have been conducted recently has remained weak because of its localized near field nature, uh, which imposes as energy momentum mismatch between electrons and light. We compared our measurements with the classical theory, which forms a bridge between the PINEM type experiments and dielectric laser accelerators. So we call them DLA in the article. DLA experiments also use phase matched electron laser interactions. However, classical theory has accurately described all DLAs experiments so far, so we know all about them. But there is a surprise that the difference in the classical versus quantum predictions appear more strongly at the maximal energy gain and loss. The first type of effect arises due to quantization of an electron of electromagnetic field. This was first analyzed by two famous scientists in 1940, just during the World War II, by Ginzburg and Sokolov in the context of the Cherenkov effect, which was already pretty extensively studied these times and was predicted to cause recoil correlations due to photon emission. To achieve a strong interaction in our experiment, we satisfy the phase matching condition by reducing the phase velocity of light using a dielectric medium, a glass prism, which we will refer a bit later. The experiment set up we used to demonstrate the strong quantized interaction is an ultra-fast transmission electron microscope. So we call them UTEM. To achieve the strong phase-matched interaction, besides synchronizing the velocities of the two beams, the focused electron probe needs to remain in the region of the invariant field over a long distance. This is achieved by gauge and angle interaction. So our experiment achieves this phase-matched interaction by eliminating the electron at the Cherenkov angle. Under this Cherenkov type phase matching condition, uh, parts of the electron wave function uh, strongly gain energy, while other parts strongly lose energy. So we talked about this previously before. So the phase velocity of light using uh, it appear more strongly at the maximum energy gain and loss. Uh, so they lose and gain energy simultaneously. In other words, the same electron simultaneously absorbs and emits hundreds of photons in our experiment. Our measurements of the electron energy spectrums reveal the quantum nature of stimulated emission uh, and the observation process of the phase-matched free electrons. Specifically, I would say we find quantum features that arise from the electron having a longitudinal wave function instead of just being a point particle. So it lasts for a distance. We can see it. And that the by applying Bynum-like formalism of an electric wave function uh, that is shorter than the optical cycle or the wavelength, the electron energy spectrum becomes similar to the classical one. So that's the main idea of the experiment. These results they conform to theoretical predictions about the dependence of the simulated emission of the quantum wave function, so of the emitting electron. That's it about the article.